In the previous chapters, we studied synchronous and induction machines operating on three-phase power systems. A key advantage of three-phase systems is that they naturally produce a rotating magnetic field, which allows motors to develop smooth and continuous torque. However, in most residential and small commercial environments, only single-phase power is available. This creates a fundamental challenge. A single-phase supply does not produce a rotating magnetic field. It produces a magnetic field that pulsates in time while remaining fixed in space. This difference is critical because induction motor torque depends on relative motion between a rotating magnetic field and the rotor. So the central question of this chapter is this: how do we produce useful torque and motion when only a single-phase supply is available? To answer this, we will study three categories of machines. First, universal motors, which are adapted from DC machines and can operate on single-phase AC. Second, single-phase induction motors, which require special starting techniques to overcome the absence of a rotating magnetic field. And finally, several special-purpose motors, which use different operating principles and are commonly used in applications where single-phase supply is available. Let us begin with the first machine in the chapter, the universal motor. The universal motor is fundamentally a series DC motor that has been modified so that it can operate on either AC or DC supply. To understand why this works, we refer back to the torque production mechanism in DC machines. The induced torque depends on the interaction between the armature current and the magnetic field. When the supply polarity reverses, both the armature current and the field current reverse simultaneously. Since torque depends on their product, the direction of torque remains unchanged. This is the key idea. Although the current is alternating, the torque remains unidirectional. If you look at figure 10.1, it shows the equivalent circuit of the universal motor, where the field and armature are connected in series. This configuration ensures that both currents reverse together, making AC operation possible. Now that we know the basic principle, we need to understand why the series connection is essential. It is important to understand why only the series motor can be adapted for AC operation. In a shunt motor, the field winding has significant inductance. This causes the field current to lag the applied voltage, introducing a phase difference between the field flux and the armature current. Since torque depends on their interaction, this phase difference reduces the average torque significantly. In contrast, the series motor has a lower inductance path, allowing the current in both the armature and field to reverse together. This is why the universal motor must be based on the series configuration, as shown in figure 10.1. With that structure in mind, let us now consider how AC operation affects the motor electrically. When operating on AC, the motor experiences inductive reactance in its windings. This reactance causes part of the applied voltage to be dropped internally, reducing the effective voltage available to produce motion. Using the relationship, EA equals K times phi times omega, we see that a reduction in internal voltage results in a reduction in speed for a given torque. So even though the motor operates on AC, its performance is not identical to DC operation. This effect becomes clearer when we look at the torque speed behavior. If you look at figure 10.2, it shows the torque speed characteristics of the universal motor. The shape of the curve is similar to that of a series DC motor, high torque at low speeds and decreasing torque as speed increases. However, the AC characteristic lies below the DC characteristic. This difference is primarily due to the voltage drop caused by reactance, which reduces the internal generated voltage and therefore reduces speed. Chapman also notes that saturation effects may influence this behavior, since peak AC voltages can push the magnetic core into nonlinear regions. To make AC operation practical, the machine construction must also be modified. To operate on AC, the universal motor must have a laminated magnetic core. This is necessary because alternating magnetic fields induce eddy currents in conductive materials, leading to power losses. Laminations reduce these losses by restricting current paths within the core. This connects directly to the concepts we studied in Chapter 1 regarding eddy current and hysteresis losses. Another important issue appears during operation: commutation. Under AC operation, commutation becomes more difficult. The alternating magnetic field induces additional voltages in the commutating coils, similar to transformer action. These induced voltages interfere with current reversal at the brushes, leading to increased sparking. This results in reduced brush life and increased electrical noise. Even with these drawbacks, the universal motor remains very useful in practice. Speed control in universal motors is achieved by varying the RMS voltage applied to the motor. If you look at figure 10.3, it shows how the torque speed curve shifts with voltage. Increasing voltage raises the operating speed. Figure 10 shows practical circuits using SCRs or triacs to control the voltage electronically. This is commonly used in tools such as drills, where speed is adjusted using a trigger. That leads naturally to the question of where these motors are actually used. Universal motors are widely used because they provide high torque in a compact form. They are commonly found in drills, vacuum cleaners, and kitchen appliances. However, they are not suitable for constant speed applications. Having completed the universal motor, we now move to the next major topic, the single-phase induction motor. Let's begin by understanding what a single-phase supply actually produces in the stator. When a single-phase current flows through a stator winding, it creates a magnetic field whose magnitude varies with time according to a cosine function. However, this field does not rotate in space. It is fixed along a single spatial axis. What changes is only its magnitude and direction over time. At one instant, the field is maximum in one direction. A short time later, it reduces to zero, then reverses direction, and reaches a maximum in the opposite direction. So the key point is that the field is oscillating in time, but it is not moving in space. So in summary, a single-phase supply produces a magnetic field described by phi of t equals phi max times cosine of omega t. This field oscillates in magnitude, but does not rotate. Without a rotating field, no starting torque can be produced. Now let's connect this to torque production. In an induction motor, torque is produced when a rotating magnetic field in stator cuts the rotor conductors, inducing rotor currents, producing a rotor field, which then interacts with the stator field. This process requires relative motion between the stator field and the rotor. But in this case, the starter's magnetic field is not rotating. It is only pulsating in magnitude. So although currents will be induced in the rotor, but the rotor's magnetic field will be always in opposite direction with the stator's field. Therefore, there is no consistent directional tendency to produce rotation. As a result, the motor cannot develop starting torque. Now let us apply that idea at standstill. We can explain this using the torque relationship between the rotor and stator magnetic fields. Torque is proportional to the sine of the angle between the rotor field and the stator field. At standstill, the rotor is not moving, and the induced rotor field will have a 180-degree phase shift with respect to the stator's field because of the Lenz's law. Therefore, the torque is zero. So from a field interaction perspective, there is simply no tendency for the rotor to move. Figure 10.6 shows this concept, and equation 4-58 shows the resulting torque from a mathematical perspective. As can be seen, the resulting torque will be zero due to the 180 degrees phase shift between the stator and rotor fields. To analyze the motor more effectively, we introduce the double revolving field theory. This theory states that the pulsating magnetic field produced by the stator in the single-phase machine can be represented as the sum of two rotating magnetic fields. One rotates in the forward direction, and the other rotates in the backward direction. Both have equal magnitude and rotate at synchronous speed. This is not a physical duplication of fields. It is a mathematical representation that helps us analyze torque and performance. Figure 10.7 demonstrates this concept. Note that the resulting stator field in this figure is always aligned with the vertical axis. Using the double revolving field theory, we can now explain torque in another way. The forward rotating field produces torque in one direction. The backward rotating field produces torque in the opposite direction. At standstill, both fields interact with the rotor equally, producing torques of equal magnitude. Since these torques act in opposite directions, they cancel. So once again, the net torque is zero. This reinforces the conclusion that a single-phase induction motor cannot start on its own. So now we begin the section on starting methods. As we established in the previous section, a single-phase induction motor cannot start on its own. At standstill, the forward and backward rotating magnetic fields produce equal and opposite torque, resulting in zero net torque. So the key idea behind all starting methods is simple. We must artificially create a rotating magnetic field during startup. Once the rotor begins to move, the motor can continue operating normally because the forward field begins to dominate. So every starting method you will see in this section is essentially a way of breaking the symmetry between forward and backward fields at startup. Let us now look at the common principle behind all of these methods. All practical starting methods rely on the same principle, creating a phase difference between two currents. If we can create two currents that are out of phase with each other, we can generate a rotating magnetic field, similar to what happens in a two-phase system. This is typically done using a main winding and an auxiliary, or starting winding. By controlling the phase difference between these currents, we create a rotating magnetic field during startup. Once the motor reaches a certain speed, the auxiliary winding may be disconnected, depending on the design. Based on this idea, three major types of starting methods exist. These are the split-phase windings method, the capacitor-type windings methods, and the method based on shaded stator poles. The first practical design based on this idea is the split-phase motor. The split-phase motor is one of the simplest starting methods. It uses two windings, a main winding with low resistance and high inductance, and an auxiliary winding with higher resistance. Because of the difference in impedance, the currents in the two windings are not in phase. This phase difference creates a weak rotating magnetic field, which produces starting torque. However, the phase shift is relatively small, so the starting torque is moderate. Once the motor reaches a certain speed, a centrifugal switch disconnects the auxiliary winding. To improve starting torque, we move to the capacitor start design. To improve starting torque, we introduce a capacitor into the auxiliary winding circuit. The capacitor creates a much larger phase shift, ideally close to 90 degrees, between the currents in the main and auxiliary windings. This produces a stronger rotating magnetic field and significantly higher starting torque. This design is known as the capacitor start motor. Like the split-phase motor, the auxiliary winding is disconnected after startup, typically using a centrifugal switch. A related design keeps the capacitor active even after startup. In a capacitor-run motor, the capacitor is not disconnected after startup. Instead, it remains in the circuit during normal operation. This improves running performance by maintaining a better phase relationship between the currents in the windings. However, because the capacitor is typically smaller than in capacitor start motors, the starting torque is lower. This design is often used in applications requiring smooth operation rather than high starting torque. Some motors combine both ideas to get the benefits of each. This motor combines the advantages of both capacitor start and capacitor run designs. It uses a large capacitor for starting and a smaller capacitor for running. During startup, both capacitors are used to produce high starting torque. After startup, the larger capacitor is disconnected, leaving the smaller capacitor in the circuit. This provides both strong starting performance and efficient running characteristics. Now let us look at one of the simplest and lowest cost designs. The shaded pole motor is one of the simplest and least expensive single-phase motors. It does not use an auxiliary winding. Instead, it uses a shading coil placed around part of each pole. This coil delays the magnetic flux in that portion of the pole, creating a weak rotating effect. However, the resulting torque is very small. Because of this, shaded pole motors are used only in low-power applications such as small fans and clocks. At this point, it helps to compare these starting methods directly. This section summarizes the different starting methods. Each method represents a trade-off between cost, complexity, and performance. Split-phase motors are simple, but provide only moderate starting torque. Capacitor start motors provide high starting torque, but require additional components. Capacitor run motors improve efficiency and smoothness. Shaded pole motors are inexpensive, but have very low performance. Understanding these trade-offs is essential for selecting the right motor for a given application. So the key takeaway from this entire section is the following. To conclude this section, all starting methods are based on one key idea: creating a phase difference between currents to simulate a rotating magnetic field. Once the motor starts, it behaves like an induction motor. The various designs differ in how effectively they create this phase shift and how much starting torque they provide. We now move to speed control of single-phase induction motors. To understand speed control of single-phase induction motors, we start with the same fundamental relationship used for three-phase induction motors. N sub S equals 120 F over P. This equation tells us that the synchronous speed depends on the supply frequency and the number of poles. However, the actual rotor speed is slightly less than synchronous speed due to slip. This means that, in practice, speed can be controlled by changing the frequency, changing the number of poles, or changing the slip. But unlike DC motors, where speed control is relatively straightforward, induction motors, especially single-phase types, have more limited and less efficient speed control options. The first and best method is frequency control. The most effective way to control the speed of an induction motor is by changing the supply frequency. From the equation, N of S equals 120 times F over P, we see that synchronous speed is directly proportional to frequency. So if we reduce the frequency, the motor speed decreases proportionally. However, this requires a variable frequency source, which is typically achieved using power electronic converters. In practice, this approach is more common in three-phase systems. For single-phase motors, it is less frequently used due to cost and complexity. A simpler but less efficient approach is voltage control. Another method of speed control is by varying the applied voltage. Reducing the voltage reduces the air gap flux, which reduces the torque produced by the motor. From the induction motor-torque relationship, torque is approximately proportional to the square of the applied voltage. So when voltage decreases, torque decreases, the motor cannot sustain high speed under load, and speed drops. This method is simple but inefficient, and it is typically used only in applications where precise speed control is not required. Another possible approach is pole changing. Speed can also be controlled by changing the number of poles in the stator winding. From the equation N sub S equals 120 F over P, increasing the number of poles reduces synchronous speed. This method provides discrete speed levels rather than continuous control. It requires special winding configurations and is not commonly used in small single-phase motors. A further method involves changing the rotor resistance. In some induction motor designs, speed can be controlled by increasing rotor resistance. This increases slip, which reduces the rotor speed. However, this method is inefficient because it dissipates energy as heat. In single-phase motors, this method is rarely used due to practical limitations. In practice, speed control of single-phase induction motors is limited compared to other motor types. Most control methods introduce inefficiencies or require additional components. As a result, these motors are typically used in applications where constant speed or limited control is acceptable. So the summary of this section is straightforward. To summarize, speed control in single-phase induction motors is based on the same principles as in three-phase machines. However, practical limitations make these methods less effective. Frequency control provides the best performance, but requires power electronics. Voltage control is simpler but inefficient. So in most applications, these motors are used with minimal speed variation. We now turn to the final section of the chapter, other types of motors. In this section, we move away from general-purpose motors and focus on special-purpose machines. Each of these motors is designed for a specific application and operates based on a unique physical principle. Unlike induction or DC motors, these machines are not universally used, but are critical in certain areas such as control systems, precision positioning, and modern electronics. We will look into 4 types: reluctance motors, hysteresis motors, stepper motors, and brushless DC motors. Each one solves a different engineering problem. Let us begin with the reluctance motor. The reluctance motor operates on a very simple idea. Magnetic systems tend to minimize reluctance. The rotor is made of ferromagnetic material but has no windings or electrical connections. When a magnetic field is applied, the rotor moves to align itself in a position where the magnetic reluctance is minimized. This alignment produces torque. So unlike induction motors, which rely on induced currents, the reluctance motor produces torque purely from magnetic attraction. That basic principle leads to a particular set of characteristics. Reluctance motors have very simple construction since the rotor contains no windings. This eliminates rotor copper losses, improving efficiency. However, the torque produced is relatively small, especially at startup. Once synchronized with the rotating field, the rotor continues to follow it, operating at synchronous speed. This makes reluctance motors suitable for applications requiring constant speed but not high torque. The next motor uses a different magnetic phenomenon, hysteresis. The hysteresis motor operates based on the hysteresis properties of magnetic materials. When the stator produces a rotating magnetic field, the rotor experiences a lag due to hysteresis. This lag creates a torque that causes the rotor to rotate. Unlike reluctance motors, the torque is smooth and continuous. The rotor does not rely on induced currents, so it avoids many losses associated with induction motors. That leads to the following performance characteristics. Hysteresis motors produce nearly constant torque from standstill to synchronous speed. This makes them very smooth and quiet in operation. However, the materials required for hysteresis operation are expensive, which limits their use. These motors are typically used in applications such as clocks, timers, and precision instruments. Now we move to a very different class of machine, the stepper motor. Stepper motors are fundamentally different from the motors we have studied so far. Instead of continuous rotation, they move in discrete steps. Each electrical pulse applied to the motor causes the rotor to move by a fixed angle. This makes stepper motors ideal for applications requiring precise position control. That operating principle gives stepper motors their special strengths and limitations. Stepper motors provide excellent position control without the need for feedback systems. Each step corresponds to a known angular displacement. However, they have limitations. Torque decreases at high speeds, and efficiency is lower than other motor types. Despite these limitations, they are widely used in robotics, printers, and CNC machines. Finally, we come to the brushless DC motor. The brushless DC motor eliminates one of the main drawbacks of traditional DC motors, the commutator and brushes. Instead of mechanical commutation, electronic switching is used to control current in the stator windings. The rotor contains permanent magnets, and the stator windings are energized in sequence to produce rotation. This results in higher efficiency and lower maintenance. Those advantages have made brushless DC motors extremely important in modern systems. Brushless DC motors offer several advantages: higher efficiency, longer lifespan, and reduced noise. However, they require electronic controllers to operate, which adds complexity and cost. These motors are widely used in modern applications such as electric vehicles, drones, and computer cooling systems. At this point, it is useful to compare these special-purpose motors directly. Each of these motors has its own strengths and weaknesses. Reluctance motors are simple but limited in torque. Hysteresis motors provide smooth operation but are costly. Stepper motors excel in positioning but are limited in speed. Brushless DC motors offer high performance but require electronic control. Understanding these trade-offs is essential when selecting a motor for a specific application. And now we can close the chapter. Chapter 10 has explored how motors can be designed to operate under single-phase conditions. We began with the universal motor, which adapts DC motor principles for AC use. We then studied single-phase induction motors and saw that they require special starting methods due to the absence of a rotating magnetic field. Finally, we explored several special-purpose motors, each designed for specific applications. Together, these machines demonstrate the diversity of motor design and the importance of adapting fundamental principles to different operating conditions.